Okay, so today's lesson will be on motion, and we move, animals move, and we want to know how efficiently you can move, okay? What's the most efficient way of moving? That's why we have coaches for athletes and all, okay? All right, so here we'll learn some of the technical details about motion, okay? We'll learn how to describe motion, okay? And what are the terms associated with it, what are the quantities that describe motion, okay? All right, you might have heard of the name Isaac Newton. He was a pretty smart fellow. Uh, he, uh, he invented calculus. He gave us the laws of motion. He discovered the law of gravity. Okay. He did very good work in light and all that. Had he done any one of those things, he'd still have been famous. He did all of that. Yeah. And look at a quote from him. Again, all these quotes are from your textbook, okay, at the beginning of the chapter. Yeah. So he says, I know not how I seem to others, but to myself I'm but a small child, wandering upon the vast shores of knowledge, every now and then finding a small bright pebble. So the law of gravity is a small bright pebble. Okay. To content myself while the vast ocean of knowledge of undiscovered truth lay before me. So again, there's a vast ocean of knowledge out there. Okay. All right, so motion is what we are interested in. Okay, we want to learn how to describe motion. So here's an example. So here's a car that is traveling along a road. Okay. Now what we are going to do is, in this chapter, we are going to restrict ourselves to one-dimensional motion. Okay. So that is objects that are traveling in a straight line. And the reason we do that is, okay, so ultimately what we are interested in is three-dimensional motion. We want to know how a bird flies, okay, and you know how your airplane flies and all that kind of stuff. You want to be able to describe that. So why are we studying one-dimensional motion? Okay. Why might we be studying one-dimensional? Okay, so here's the reason. It turns out, so let's say you fly on a plane like that. This motion, okay, here's the x-axis, here's the y-axis, here's the z-axis. When a bird flies, the projection of this motion along the x-axis, did you guys understand that? So if you shine a light on that, the shadow of this motion along the x-axis, that's a projection along the x-axis. The projection along the y-axis and the z-axis are independent. Okay. This motion is a combination of those three motions. Okay. So if you learn to describe motion along one dimension, then you can describe any motion in three dimensions. Okay. So that we keep things simple. Okay. When you eat a steak, you eat the whole steak. No, you eat it one bite at a time. So this is one bite. All right, so we are going to describe motion in one dimension, because once we understand motion in one dimension, then we can combine motion in several independent dimensions to make a complex motion. Okay, so here's we want to describe the motion of this car. Okay, so it starts off there, goes forward, and then it goes back, like that. All right, it turns out, so we want to describe this as efficiently as possible and in a very useful manner, okay? And it turns out a graph is a useful description, okay? So here's what the graph is doing, okay? So this line is represented by the x-axis, so we'll draw an axis. Okay, so there is the origin, there is the zero, there's the origin. There is the x-axis pointing in this direction. In this direction, distances are positive. or positions are positive, locations positive. In that direction, locations are negative. Okay. All right. And this is time. Okay. So what is this graph representing? It's telling you at 0 seconds, the car is at 30 meters. Okay. At 10 seconds, the car is at 50 meters. At 20 seconds, the car is back at, let's say, 37 meters. Okay. So you can see that at any time, so if you want to ask where's the car at 23.5 seconds, go to 23.5 seconds. There's the car. It's at 25 meters. Okay. So this is a complete description of the motion. You know exactly where the object is at all times. Okay. So, another way to do this is, okay, so you can describe a motion by giving the graphically giving the location of the object. Here's another useful way of doing it, giving the position of the object as a function of time. Okay. So here's a complete description. So let me give you a couple of examples. So here's okay, so here's one motion described to you, okay, mathematically. Okay. Here's another motion. How many different types of motions are there? Okay, so here's one motion. Another motion. How many different types of motions are there? No. Is there only two ways I can walk? No. So, I'm sorry? There's an infinite different number of motions, okay? And you can describe them. Okay? So here's mathematically how to describe this motion. I'm going to drop this object. Okay. This motion, if I dropped it at 0 position, its position as a function of time is given by this formula. As soon as I get hold of my pen. Okay, and that is the acceleration due to gravity. Okay, so this is 4.9 t squared. And now not written units there. So here's a mathematical description of a freely falling object. Okay, okay, so that's what we're interested in describing motion. Okay. All right, so the subject of study of motion is called kinematics. Okay? So a description of motion. You learn that we'll define terms like velocity and stuff like that. Okay, so to change velocity, what you have to do is you have to apply forces. Okay, and we'll learn about that in the next chapter. Okay, and that's called dynamics. All right. Now we want to understand the terms vectors and scalars. All right, so let me give you two pieces of information. Let's say I'm going at 50 miles an hour. That's one piece of information. And I'm going at 75 miles an hour north. What is the difference between the two? Direction, very good. Okay, so in the second piece, okay, there was direction as well. Okay, so quantities that have magnitude and direction, they're called vectors. Quantities that have only magnitude are called scalars. Okay, so when I gave you my speed and direction, that is called velocity. Okay, and those are represented by vectors. When I just gave you speed, all I need was one number. I'd tell you how fast I'm going. I didn't tell you what direction I'm going in, okay? So vectors are quantities that are represented by directed line segments. arrows. Okay. And scalars are quantities that all you need is one number to specify them. Okay. These guys are vectors: velocity, acceleration, displacement. All these quantities are vectors. Okay. So you need magnitude and direction to specify them. Okay. It turns out that for vectors in 3 dimensions, you need 3 numbers to specify them. In 2 dimensions, you need 2 numbers to specify them. Scalars, on the other hand, it doesn't matter how many dimensions you are in, all you need is 1 number to specify them. Okay. So scalars are, so speed, pressure. Can you think of any other quantity that you need only 1 number to specify? Temperature. Okay. So, and so on. Okay. All right. So we will learn quantities that are vector quantities, and we'll learn about quantities that are scalar quantities. Okay. So we'll learn about quantities that need more than 1 number to specify them. Okay. So vectors are quantities that have have magnitude and direction. Okay. And in 3 dimension, you need 3 numbers to specify them. So 1 number for magnitude and 2 numbers for direction. Okay. In 2 dimensions, you need 1 number for magnitude and 1 number for direction. In 1 dimension, okay, so in our example of that straight road, in 1 dimension, vectors can point only this way or that way. Okay. So for direction, what we use is sign. So for instance, this can be a speed of velocity of 10 meters per second, and this is minus 5 meters per second. So you see the direction is given by the sign. Okay. You don't need an extra number. So 1 dimension is special. All right. All right, so again, we are trying to describe motion. Okay, so let's look at this armadillo. He's going for a walk. And again, right now we're going to restrict him to travel in a straight line. Okay. And how are we describing this motion? By giving you this graph. Okay. This graph is describing this motion. His position is given on this x-axis. There is the origin. There is the positive direction of the x-axis. So the position is the location of the particle with respect to a coordinate system. Okay? So the position tells you where the object is. Okay? So again, let's make sure we understand this. So there's time in seconds. At 0 seconds, the armadillo is at minus 5 meters. Minus 5 meters, there's 0, there's minus 5 meters. So if minus 5 meters is roughly from the distance from here to the wall. So that was the 0, and our axis is pointing in that direction. Here is the armadillo. Okay. All right, that's what that's telling you. Okay. And then at 1 second, armadillo is minus 4 meters. So the armadillo traveled 1 meter in 1 second. Okay. And that's not realistic. I don't think armadillos walk that fast, but anyway. At 2 seconds, the armadillo is at minus 2.5 meters and so on. Okay. Anyway, so see, this graph tells you exactly where the armadillo is at all times. Okay, which is what my mother wanted to know about me. Okay. So this is one. Okay. So all right. So mathematically, a motion of an object can be described by giving the position as a function of time. So if somebody asks you to describe a motion, this is what they're asking you technically. Okay? All right, let's understand the displacement. This is a vector. Okay, so a vector is represented by a line segment, a directed line segment. Okay, and so we'll come back to this one-dimensional example in a second, but let's do a 3D example. So X, Y, Z. Yeah. So let's say we are looking at a bird flying. Okay. So this is the initial position of the bird, and there's the final position of the bird. Okay. The displacement vector is a vector that points from the initial point to the final point. This is the displacement vector. Okay. Now let's say if the bird flew like that, what is the displacement vector? It is still the same. Okay, so you can have a billion different flights, and the displacement vector would be the same. Okay. All right. You started at home. After all your classes, you reach back home. What's your displacement vector? 0. Right? You came back to your initial spot. You went to New York, you started at home, went to New York, and came back home. What's your displacement vector? 0 vector. Okay? All right. So a displacement vector does not give you any details of the path. All it is a vector pointing from your initial point to your final point. Okay? But it is a vector. Okay. So now let's come back to one dimensions. Okay. So in this picture, time is increasing this way. So this event happened first, and this event happened later. Okay. So anyway, this lady is starting from home, and she walks half a kilometer that way and then walks back. Okay. So what was our path? There was our path. There's the initial point and the final point. And the displacement vector denoted by delta x, okay, change in the position, it was just equal to the final position minus the initial position. Okay. And in this case, this happens to be that, and the displacement was 0 for this walk. Okay. How about for this walk? Here's the second walk. She started here, went 1 kilometer there, and then came back 1.75 kilometers. What was the displacement vector for this walk? There's the initial position, there's the final position. Okay. All right, this displacement was, so if you put in, if this was 0, this location was 0, the final location, this final location will be minus 0.75 kilometers. Yeah. So x2 minus x1 minus 0.75 kilometer minus 0. Okay. What does the minus tell you? That the net displacement is to the left. And what does 0.75 kilometers tell you? It tells you the length of the displacement from the starting point. Okay. All right. Again, this is a vector, and it's a vector pointing from your initial point to your final location. Okay. Okay, displacement is a vector. Distance is a scalar. All right, so let's look at the same paths again. Okay, for this motion, the displacement was 0, but the distance traveled is not 0. The distance traveled is the actual distance traveled. Okay, so distance traveled will depend on the path taken. Okay? And so for this, the distance was, the first one distance was 1 kilometer. What was the distance for the second motion? What was the distance for the second motion? 1 I'm sorry? No, 1 plus 1.75, 2.75 kilometers. Okay. So distance for the second one was 2.75 kilometers. Okay, so distance is the actual distance traveled, and that depends on the path taken. So you go from, you start from home, come to school, and go back. Displacement was 0, but the distance is not 0. Okay? And the distance for that was, well, depends on how far you're living. You start from home, go to New York, and come back. Displacement was again 0, but distance is again different. Okay? So distance depends on the path taken. Distance is a scalar. All right, now we'll define velocity. Velocity is a vector. Yeah. It has magnitude and direction. Magnitude tells you how fast you're going, and direction tells you what direction you're going in. Okay, so velocity is a vector. Average velocity is defined as displacement divided by the time over which that displacement happened. Okay. So let's say you go from, start at home, go to school, and come back. What is your displacement? 0. What is your average velocity? 0 divided by 2 hours, 0. Okay. You started at home, went to New York, came back home. What was your displacement? 0. Okay. It doesn't matter how long it took you. Your average velocity was 0. Okay. All right. But oftentimes we'll be interested in instantaneous velocity. Okay. So for instance, you're driving on 95. Your speed is whatever your speedometer says, and the direction is the direction in which you're driving. So if you're driving north at 80 miles an hour, there's your velocity. Okay? And if you're driving east at 50 miles an hour, there's your velocity. Okay? And your speedometer tells you the length of this vector, and the direction tells you the direction in which your velocity is pointing. Okay? All right, the units are, this displacement is measured in meters, that's in seconds, meters per second. That's the units for velocity. Speed is distance traveled divided by the time. Okay. You start at home, go to school, and come back. What was your average velocity? 0. You start at home, go to school, come back. Distance traveled was not 0. Okay. Average speed is not 0. Okay. All right. Acceleration, that's a vector. When are you accelerating? When do you accelerate? What does the word acceleration mean to you guys? I'm sorry? Yeah, so when velocity changes, then you're accelerating. Okay. Okay. Okay, so let me do a couple of examples. Okay. All right, so here is we'll represent velocity by that. So the subscript just tell you the velocity at different times. So let's say you're driving east on some road, I-4 or something like that. In this case that I'm describing, are you accelerating? Are you accelerating? Okay. See, the velocity is constant. You're not accelerating. Okay? Acceleration is 0. Did you guys understand that? Okay. So velocity Velocity was a vector. It has magnitude and direction. The magnitude is not changing. The length of the vector is not changing. The direction of the vector is not changing. You're not accelerating. Okay? All right. How about now? What have I drawn? What is happening? I'm sorry? Yep, very good. Okay, so your direction has not changed, but your speed has changed. Okay, so velocity changed. So you're accelerating. And in this case, the acceleration is pointing in the same direction. Okay, and it's not equal to 0. Okay. Okay, what's happening now? Yes, so your velocity, I'm sorry? Your speed is decreasing, okay? Your direction is the same. You are accelerating, okay? When does this happen? When you're trying to stop your car, when you apply brakes, okay? And so, in this case, the acceleration is in the opposite direction, okay? And it's not 0. So if velocity was positive, then the acceleration would be negative, okay? So it's pointing in the opposite direction. All right, so here was, what did we do? We changed the magnitude of the velocity. We changed your speed, okay? So now let me give you a tricky one, okay? So think before you answer this question. So here's a circular road, okay? I'm going to drive on it at constant speed. So V1, V2, V3, V4. And the speed, let's say it's 10 meters per second at all times. Am I accelerating? What's that? All right. So, I'm sorry? Okay, so what is velocity? Velocity is a vector. It has magnitude and direction. You accelerate anytime the velocity changes. Okay? All right, we didn't change the magnitude, but what did we change? We changed the direction. Okay, so you are accelerating. Okay. So even though your speed is constant, your direction is changing and you're accelerating. And it turns out that the acceleration is in this direction, towards the center of the circle. All right? In the next chapter, you'll learn if you want this acceleration for an object of mass m, you have to apply a force like that. Okay? All right, so for instance, so let's do an exam. Let me tell you put some numbers here. Okay, so if this was Earth, the Earth is going around the sun. Okay. The Earth is going around the sun at 30 kilometers a second. The Earth will get from here to about Daytona Beach in 1 second. That's how fast it's going. Okay. And obviously the Earth is accelerating toward there. So what is applying a force on the Earth to make it go around in a circle like that? Very good. That's the sun's gravity. Okay, so the gravitational force of the sun is making the Earth go around. Okay. All right, so here's a thought experiment. So let's say you go home after this class and you flip a switch and make the sun vanish. What will happen? I'm sorry?
Can you say that again?
All right. So you get up, you flip a switch, and you make the sun vanish.
The sun down.
Yeah. You can't do that? Poof, the sun is gone. What will happen? What's that?
No, should all die.
We should all die. Well, before we die, what happens? Okay, so if you remove the force, you remove this force, you cannot have this acceleration anymore. And so, no, it won't go around, it'll go in a straight path. Okay, you remove the force and the velocity won't change anymore. Okay, so it will go in a straight line. And you've seen this, you tie a rock to a string and whirl it around. As long as the string is exerting a force on the rock, it'll go in a circle. If the string breaks, the rock will go in a straight path. Okay? All right. All right, so what this formula says is you have an acceleration whenever the velocity is changing. If the velocity does not change, your acceleration is 0. Okay? And you saw how velocities can change. You can either change the magnitude or the direction of velocity. Okay? Okay, so what this graph is showing you is if you plot velocity as a function of time, you can calculate the velocity at acceleration at any instant. It's the slope of that tangent line. Okay? The acceleration is the slope of that tangent line. Okay? So for instance, at this instant, the acceleration is positive. Here it's 0. Here it's negative. Okay? But we won't worry about that. All right, so we saw this, a combination of velocity and acceleration. So here's a car whose velocity is not changing. The acceleration is 0. Okay? Here's a car whose velocity, the magnitude of the velocity is increasing. Okay? So acceleration is pointing in the same direction. So if you're speeding up, your acceleration is pointing in the same direction as the velocity. If you're applying brakes, the velocity is decreasing, your acceleration is pointing in the opposite direction. Okay? Okay, so again, we'll be talking about 1D motion. What does 1D motion mean? Yeah, one dimension, so you are traveling in a straight line. Okay? So we'll look at 1D motion with constant A, constant acceleration. What does that mean? Acceleration is not changing with time. Okay, and this is one of the few motions, freely falling. Okay. This has a constant acceleration. The acceleration is the acceleration due to gravity, and it's 9.8 meters per second squared. Yeah. And even this is hard to maintain for any length of time. In half a second, it hit my arm. Okay. I can throw it from the top of the building. That motion will be over in about 2 seconds. Okay. All right, so, but that's what we'll talk about. Motion, we'll look at 1D motion with constant acceleration. So here's a graph. So here's acceleration as a function of time. And you see, acceleration is constant. It's not changing. Okay? So that's what we're going to look at. So if you have motion with constant acceleration, so for instance, you can start off your car on a straightaway and start accelerating. You will be able to maintain constant acceleration maybe for 1 or 2 seconds. Okay. Yeah. While your acceleration is constant, your velocity increases linearly. Okay. And if the acceleration is pointing in the opposite direction, it'll decrease linearly, but your velocity changes linearly. Okay. And your position changes quadratically. So if you maintain constant acceleration, this is the type of motion that you have. Okay? Okay, so 1D motion with constant acceleration. We want to learn these 3 formulae. Okay? You don't have to memorize it. I'm going to tell you what they are, and I'm going to show you how to use them. Okay? And you just have to have a sense for that. Okay? All right, what this tells you is this is your final position. X naught is your position at time 0. That's what the subscript tells you. What is V naught? That's your initial velocity, velocity at time 0. Time plus 1/2, that is acceleration times t squared. So what this formula does is it tells you where you are at this time. It tells you your position as a function of time. Okay? Again, so final position minus initial position is displacement as a function of time. Here's another formula for displacement. That's equal to the average velocity times time. Again, we won't use this too often, but that's what that is. Okay. What is this formula? This gives you the final velocity. This is your initial velocity plus acceleration times time. So this will tell you how fast you'll be going after that amount of time. Okay? What does this formula give you? The final velocity square is equal to the initial velocity square plus 2 times the acceleration times the displacement. So this tells you how fast you're going after having traveled that distance. Okay? So this tells you how fast you're going after a certain amount of time. This tells you how fast you're going after having traveled a certain distance. Okay? All right, so these formulae work only when the acceleration is constant. Okay? And here's an example of a constant accelerated motion, a freely falling object. Okay? A freely falling object is an object that is only falling under the influence of gravity. Okay? So this is a freely falling object. Can I shoot a bit? Can I have a sheet?
Yeah.
All right. So here's an object where gravity is the only force acting on it. Okay? That's a freely falling object. And its acceleration is 9.8 meters per second squared. And we'll come to that number in a second. How about this guy? Was that freely falling? Why not?
So, yeah, it's pretty sure, but it's so
So what happened?
Have more resistance.
yeah.
The air resistance was not negligible, so there were multiple forces acting. So the difference was effectively on this guy, gravity was the only force acting. There was air resistance, but it was negligible. Okay. So that's what a freely falling object is. Okay. All right. So the magnitude of the constant acceleration, acceleration due to gravity, we use a special symbol g, okay, but that's acceleration. It's 9.8 meters per second squared. Okay, what that means is the following. So let's say you drop an object. Its velocity at 0 seconds will be 0 meters per second. After 1 second, it's going at, so g is 9.8 meters per second square, meters per second per second. That means the velocity increases by 9.8 meters per second per second. So after 1 second, it's going at 9.8 meters per second. After 2 seconds, how fast is it going? Very good, 19.6 meters per second. Okay. After 3 seconds, it's going at 27. Okay. Let's see. After 3 seconds, it's going at 29.6 meters per second. Okay. Now this is 10 meters per second is roughly 25 miles an hour. Okay. So I drop this keychain. After 1 second, it's going at 25 miles an hour. Okay. After 2 seconds, it's going at 50 miles an hour. Okay. After 3 seconds, it's going at 75 miles an hour. No sports car accelerates that fast. Okay? You want fast acceleration, you have to drive it off a cliff. Okay? And you can drive any car off a cliff and it'll accelerate at that rate. Okay? So this is a large acceleration. Okay? All right. So this tells you, so for a freely falling object, and this is the initial velocity. If you give that initial velocity after 1 second, it'll be there. After 2 seconds, it'll be there, and so on. Okay. Now, okay. Now I'll solve a couple of problems. Okay, you just need to be aware of that. And on the test, maybe there might be 1 or 2 problems, and I've just changed the numbers. Okay, so all you have to be is aware of this. Need to know this. Okay. So this problem says, a sprinter is able to produce an acceleration of 8 meters per second squared. So that's the acceleration. For the first 0.75 seconds of the race, okay. Calculate the velocity of the sprinter at 0.75 seconds, okay. If she starts from rest, and part B has a running start of 1 meter per second, okay. So let's do part A. So what are they asking you? Calculate the velocity of the sprinter at 0.75 seconds. Okay, so we are going to use one of these 3 formulas. Okay, and since they're asking for velocity at a certain time, so this is the formula we want to use. Okay. All right. So velocity. Okay, so there's the final velocity, there's the initial velocity, acceleration times time. Okay, so initial velocity for part A was 0. The acceleration is 8 meters per second square. And what are you trying to do? You're trying to find how fast will the sprinter be going at 0.75 seconds. Yeah? And this is equal to, okay, 1 of the seconds cancels, okay, and 8 times 0.75 is 6. Okay. So the sprinter is going at 6 meters per second. And if a problem like this is on the test, all I've done is change the numbers. That's it. Okay. Part B of the problem says, okay, what is the velocity? Has a running start of 1 meters per second. So that is the initial velocity is 1 meters per second. That fellow is 1 meters per second. Okay? So part B, V equal to V naught plus AT. That is 1 meters per second plus 8 meters per second square. That is 1 plus 6 equal to 7 meters per second. Okay. So after the same time you're going faster, that's because you had a running start. Okay. All right. Any questions on that? All right, so this is, okay, so let's look at this problem. So a tennis ball is hit straight up with an initial speed of 30 meters per second. Okay. So 30 meters per second is roughly 75 miles an hour. Okay. Where is the tennis ball relative to the tennis racket 2 seconds after it's hit? So they're asking you, where is the tennis ball? So they're asking you for the position of the tennis ball. Okay. So this formula involves position as a function of time after a certain time. And so that's the one we'll use. Okay. All right. Now what we'll do is we'll have to draw an x-axis. So this will be our x naught, and again that'll be. So you're shooting it with an initial velocity of 30 meters per second. Okay. You hit it with a velocity of 30 meters per second. Which way is your acceleration pointing? So let me toss this object. What was happening to it as it's going up?
Slow down.
Slowing down. That's because the acceleration was pointing this way. Acceleration due to gravity always points towards the ground. Okay, so this is the direction in which. What is acceleration due to gravity? 9.8 meters per second square. Okay, except that this vector is pointing that way, so this is negative 9.8 meters per second square. Okay, so we chose this direction to be the positive direction, okay, the upward direction. So this vector pointing in the other direction is negative 9.8 meters per second square. All right, now let's look at the problem. Okay, so where is the tennis ball relative to the racket 2 seconds after it was hit? Okay, so here is x minus x naught equal to v naught t plus 1/2 acceleration times t squared. Okay, we are trying to find where was the object after 2 seconds. T is 2 seconds. Okay, the initial spot is, we'll take that to be 0. Okay, all right, so what we're trying to find is x minus 0. What is the initial velocity?
Mm-hmm.
30 meters per second. Okay, so that's 30 meters per second. At what time are you trying to find where it is? 2 seconds plus 1/2 acceleration is negative 9.8. Okay, 2 seconds squared. Okay, so this is where the object is at 2 seconds. Okay. The seconds cancels. 30 times 2 is 60 meters. Okay. And this is 9.8 divided by 2 is 4.9. So minus 4.9 times 4. Okay. Again, the second square cancels with that. Okay. And this all works out in meters. So this is 60 minus 5 times 4 is 20. So 19.6. Okay. So you hit a tennis ball, 2 seconds later, it's 40 meters up. 40 meters up is half a football field length. Okay. So, or you get a baseball player to throw a ball straight up. Okay. They can throw it 75 miles an hour easy. Okay. In 2 seconds, the ball will travel half a football field high. Okay. And that's what we calculated. Okay. What is its velocity 2 seconds after it was hit? So now you're asking for velocity after a certain time. Okay. And if you look at the formula, this is the one you want. Okay. This gives you final velocity is initial velocity plus acceleration times time. So here is your initial velocity. So what is happening to the velocity? It's slowing down as it's going up, right? So the final velocity should be less than 30 meters per second. Okay. Plus acceleration was 9.8 meters per second. 2 seconds. So you shot the ball up at 30 meters per second. After 2 seconds, it's going at 10 meters per second. Okay. So this problem is worked out in, I mean, we've already done it. So it travels 40.4 meters up, and the final velocity is 10.4 meters per second. Okay. All right, guys, so that finishes this chapter. Okay.